All right, so we got some vectors. What can we do with them? The answer turns out to be a lot, but in this segment we're just going to learn three things, three different operations that are very commonly performed on vectors and scalars together. And here they are. The first is scalar vector multiplication. So that is a way of taking a scalar and multiplying it by a vector. Another is vector addition, which is adding together two vectors. And the third one is vector multiplication, multiplying together two vectors. Now, two of these, I'll just tell you right off, are going to seem very obvious, and they are. The other one is going to seem strange, and it's not going to seem like the right thing at all, and I'm talking about that third one. So when we get to that, kind of heads up that the result of multiplying two vectors is almost certainly not going to be what you expect it to be at first, but it's going to turn out to be the useful thing, which is why it's defined that way. By the way, you will notice on this list something absent, and that is scalar vector addition. So what about taking a scalar and adding it to a vector? It turns out we can't do that. It turns out that's not a thing, and that's just going to be because of how we define it. So if we define a couple things here, let's define A, and we'll say A is 3. And we'll define a vector x, and we're going to make it very simple to start with. We're going to say 2, 1, and -4, right? Perfectly valid vector. So what do I get if I take a plus x? The answer is nothing. Can't do that. So we're not going to define a way to add a vector to a scalar. Now, when you get into programming languages like R or Python or virtually any others, they will allow you to do this and give you something meaningful back. But it's important to understand, I guess, from the standpoint of linear algebra and what it means, that that's purely a little convenient shortcut they give you. Like if I wanted to add the number 3 to each element of the vector, R and Python will both allow me to say A plus X, and it will give me back 5, 4, -1. But that's not an important mathematical operation. That's just sort of a programming language convenience. So I'm sticking here with the things that really do matter in a deep sense to linear algebra and what it means. All right? Okay, so we can't do that. What we can do, though, is this. Ax, and that's scalar vector multiplication. And what we're going to get out of that is probably what you'd expect. We're going to get 6, 3, -12. So when we do scalar vector multiplication, all you do is multiply the scalar by each of the elements of the vector, 3 times 2, 3 times 1, 3 times -4, and we get out this composite vector right here. It's not surprising that if I say 0 times x, I'm going to get 0, 0, 0. And it's not surprising that if I do 1 times x, I'm going to get back x itself, which is 2, 1, -4. Simple stuff. So that's how you multiply a scalar and a vector together. Vector addition is just as easy. If we take two vectors here, we're going to say 2, 1, -3, and we're going to take 5, 0, 5. What does it give us if we take x plus y? And it won't surprise you, I'll bet, to learn that the answer is 7, 1, 2. All we do is we add each of the components of the vectors individually to arrive at the answer. 5 plus 2 is 7, 1 plus 0 is 1, -3 plus 5 is 2, and so it's just as easy as that. You might wonder, what if they're not the same length? Like what if I say I've got z is equal to 2, 5? So it's only got 2 elements to it. Then what do I get when I do x plus z, for instance? And the answer is can't do that. So you might think that we would say, well, let's add 2 and 2, and then let's add 1 to 5, and then let's just say -3 gets stuck in there by itself since there's nothing to add it to. Yeah, that makes sense, but no, not a thing. We're going to say that mathematically speaking, you can't add two vectors together unless they have the same length. And by the way, if we're dealing with vectors that aren't indexed by number, then actually their whole domain has to be the same in a function sense, right? So we said that, if Jeff is, 36 years old, and if Bev is 21 years old, I'm kind of making this example up, which is kind of dumb. Doesn't really make sense to add years oldness, but if I say Jeff grew 3 years since I saw him last, and Bev grew 4 years since I saw her last, maybe that makes sense to say what's x plus y? Well, it's going to be Jeff is now 39 when I see him again, and Bev is 25 when I see her again. So that's what that would mean there. And if we said z was equal to Jeff was I saw him last 4 years ago, and we said that Thomas was one. I saw him 1 year ago, and then we asked, what is x plus z? Again, the answer will be nothing. Can't do that. And that's because the domains are not the same. Jeff and Bev is not the same as Jeff and Thomas. Therefore, even though they have the same length, you can't meaningfully add the two together, right? So basically, you're just going to add the ones that have the same name. If they don't have the same names, then we call the whole thing off, and we can't even do the operation. Okay, so those are the first two. That's multiplying a scalar by a vector, and that's adding two vectors. Now, the one that's weird is this, multiplication. And we have a special name for that, and the name is called the dot product. And you will hear me use that term a lot. You'll also hear me use the term inner product, and it turns out those mean basically the same thing for our purposes. It turns out that dot product is a special kind of inner product, and you can define other types of inner products. That's a little far afield for what we want to do, though. So we're going to essentially consider these two terms synonymous. But here's the thing. So remember when we took a scalar times a vector, we got back a vector, right? So if a, let's make a equal to 5 here, right? So we got back 10, 5, 15. So a scalar times a vector gives us a vector. That might have seemed surprising to you, I'm not sure. It turns out that when we multiply two vectors together, we get back a scalar, weirdly. So wouldn't you think that this would give me something like 6 to negative 12? Wouldn't you think I'd multiply the first two together, and I'd multiply the second two together, and I'd multiply the third two together, and then I would get a vector back, which would be the multiplications of each of those three things? Yeah, you totally think that. No, it's not what it is, though. What it is a scalar back, and it's essentially going to be the scalar that's the sum of those things. So I'm going to take 2 times 3 plus 1 times 2 plus 3 times negative 4. Okay? So in other words, I am going to take each pair of things and multiply them together. But my final answer is not the vector that contains those three elements. Rather, what I'm going to get back is the sum of those three different things. So I'm going to get 6 plus 2 plus negative 12, which is going to be maybe negative 4. Is that what that works out to be? I feel like maybe it's negative 4. So whatever it turns out to be, if you do the math, that is what the answer is going to be to the dot product. So whenever you take the dot product of two vectors, you always get back a scalar, which is the sum of each pair of elements multiplied together in tandem. And just as with just as with vector addition, we're not going to allow you to multiply two vectors together unless they have the same domain, which boils down to having the same length if we're indexing something by index, right? So again, if I say x is the vector 2, 3, and I say y is the vector 1, 1, 1, then I'm going to say x times y equals no. You can't do that. Okay, so we'll talk a lot about those different operations, and those sort of form the wheelhouse of what you can do with vectors under the hood. And there's a lot of other things that we're going to add to that, but these three really are kind of like the alphabet soup of dealing with vectors and scalars, right? So I think the most critical one to understand is dot product and how that might be different than what you might have thought it was, all right? Let's do some quick review. So if you haven't done all the math before, in most of the episodes I'm going to have little quick review segments, which basically I'm going to give you a question, ask you the answer, and what you need to do, and it really does matter if you do this, okay, is to pause the video when I say to pause the video and work out the answer on your own. Then resume the video and make sure you got the right answer, okay? It's going to be tempting. You're going to be tempted by the dark side to just let the thing run, let the video run without pausing it, because it's going to go faster that way. And I'm going to tell you what each answer is. You're going to say, yeah, I knew that. Yeah, I knew that. But I'll tell you right now, some of them you're going to fool yourself into thinking that you would have gotten that answer had you paused the video, but really you wouldn't have. And the only way to really cement this stuff in your mind, I've found, is to actually pause the video and make you do the exercises. And then you'll see, whoa, I thought the answer was 19. He got negative 17. Why is that? And then you hear my explanation, and then that really reinforces what the right thing is in your understanding. All right, so enough lecturing. Let's get to the quick review. So our first question here is, I've defined some things, A, B, C, and D. I've got A being a scalar and B being vectors. And my question is, what is A times B? So this is your first chance to pause the video right now, figure out the answer, then resume and see if you're right. Okay, now that you've resumed the video, you will see the answer is 802 because scalar multiplication is simply multiplying the scalar by each of the elements of the vector in turn, and what we get back is a vector when we do a scalar times a vector. What if we do b plus c? Pause the video and figure it out. The answer there is going to be 7, 3, 4 because we get 7 is the first element, 4 plus 3, then 3 which is 0 plus 3, then 4 which is 1 plus 3, easy as pie. What about c plus b? What do we get? And the answer is 7, 3, 4, which is the same thing we got a minute ago. Hey, that's kind of interesting. When I did b plus c, and then I did c plus b, I got the same answer. You think that's always going to be the case? The answer turns out to be yes. The proof is very simple. If you want a proof, you can basically just work it out. It comes down to the definition of what addition of vectors are, and you will see that it's going to always be the case that a vector plus a vector is the same as that second vector plus the first vector. In fact, that is called being commutative. The vector operation of addition is commutative. Heads up on that because we're going to come up with something in the next episode which seems like it would be commutative but is not. And it's very important to understand that it's not commutative. This thing here, though, vector addition, turns out to be commutative. All right. What is b plus d? Pause the video, figure it out. And the answer is can't be done. We cannot do that that operation. You can only add two things together if they have the same length or if they have a named domain, if they have the same domain. What about a plus d? Again, cannot be done. You cannot add a scalar to a vector. Programming languages let you do that as a convenient shortcut for certain mechanical operations, but it's not a meaningful mathematical thing to do that. So it's safe to just say the answer is nothing. All right, what if we take c plus b and then we multiply the answer by a? What do we get? And that's going to be 14, 6, 8, because if you take c plus b, as we did a couple slides ago, you get 7, 3, 4. And if you take 7, 3, 4 and scalar multiply that by 2, you get out 14, 6, 8. All right, what's this one? Let's take a times c plus a times b. What do we get? And the answer is we get 14, 6, 8, because if you multiply a times c, you end up getting 6, 6, 6, the number of the beast. That was an accident, I promise. Plus a times b, and you get back 8, 0, 2. You add those together, and you get 14, 6, 8. Hey, that's funny. When we did a times c plus b in parentheses, we got the same thing as we did when we got a times c plus a times b. You think that's always going to be the case? Turns out, again, the answer is yes. And the fancy mathematical way of saying that is that scalar multiplication is distributive when combined with vector addition. So the operations of scalar vector multiplication and vector addition turn out to be distributive. Therefore, you can always count on those two answers being the same. All right, back to work. What's c minus b, do you think? I never actually said what this was, but see if you can figure it out. And the answer is negative 1, 3, 2, because c minus b just means subtract each of the elements off of b when you do the addition, right? So if you want to think of this in terms of what we have learned, if I take, x being 1, 3, 9, and if I take y being 2, 2, 2, if I say x minus y, that's really the same thing as saying x plus negative 1 times y. And we know how to do that, right? This here is scalar vector multiplication. And so we know that if we multiply those two things out, we're going to get negative 2, negative 2, negative 2. And then we can do x plus that, and we're going to end up getting negative 1 and 1 and 7, I believe, right? So when you do a subtraction operation, that's really just the same as multiplying the second vector by negative 1 and then doing an addition. So it turns out to be very intuitive. All right, dot product. This is the guy that's a little bit tougher to figure out. So do some practice. What is b dotted with c, or also known as b times c? Pause the video, figure it out. You're going to get 15 in that case because 4 times 3 is 12. 0 times 3 is nothing. 1 times 3 is 3. Therefore, you add up those different products and you get the sum of 15. Let's do it the other way. C times B, what do we get? In that case, we get 15. Hey, that's funny. We did B times C and got 15, then we did C times B and got 15. You think those will always be the same? Answer is yes, and that's because vector multiplication, also known as dot product, is commutative. Again, you can do the multiplication in either order, guaranteed to give the same result. If you want a proof, just work it out and you'll see that you're doing the same thing algebraically in each case. All right, what about C times D? What does that dot product give us? And the answer is can't do it because those two do not have the same size. Cannot do a dot product of two vectors unless they have the same length or the same domain. What about D times D? Can we do that? Yes, we can, and the answer is 20. You can always multiply a vector times itself because it's always going to have the same length as itself or the same domain as itself. Duh. All right, let's do some more complicated examples here. We now have some recipes, and we've got the recipe for chocolate chip cookies. By the way, don't try to make these at home. I do not guarantee that this is at all right. I kind of made up some stuff. I also don't have vanilla in there or baking soda or some other necessary ingredients, so please just treat this as a mathematical exercise. Question, how can I form a vector operation that would give me the answer to my question I have here? I want to know what my shopping list needs to be. I want to make 5 recipes of chocolate chippers. I want 3 batches of fudge. How would I express that in a vector operation? The answer is this. I would take 5 times the chippers vector plus 3 times the fudge vector, and that would give me my combined shopping list. Think that through to make sure you understand why. If you take the vector of the chippers and multiply it by 5, that's essentially going to multiply every element by 5, which is going to give me another vector which tells me how much of each ingredient I'm going to need to make 5 chocolate chippers. And then it's just a matter of doing that for the fudge, adding them together. And the final thing is going to give me back a vector which tells me I need 16 sticks of butter, 11 cups of sugar, 17 packs of chocolate chips, 5 cups of flour, and 15 eggs, or whatever it turns out to be. What if I want to know how much it would cost to make something here? So I want to make 5 chippers, 4 pans of brownies, 5 batches of fudge this time. How would I represent in a vector equation how much that would cost if I go to Wegmans, say? So you'll notice I have the Wegmans vector, which is telling me how much a stick of butter is, how much a pound of sugar is, how much a package of chocolate chips is, etc. How would I express this in a vector term? And this is what I'm going to get here. So I'm taking 4 times the chippers vector, plus 8 times the brownies vector, plus 5 times the fudge vector, add all those together. That gives me my combined shopping list, which I'm taking to Wegmans. It tells me how many sticks of butter I'm going to get total, how many pounds of sugar I'm going to get total, etc. Now I'm going to dot product that by the Wegmans vector. And if you think that through, that is going to take each of the ingredients. It's going to multiply the number of them I need times the per unit cost, and then add all those up together. So you can see this thing's tailor-made for doing operations like this. Combine the 3 recipes, each of which is multiplied by how many batches I want of that recipe, then dot product it by the thing, and I'm going to end up getting my combined recipe dot producted with Wegmans. So that's doing the first step there. And then the final answer is going to be a scalar, which is how many dollars it takes. Who knew it would be that expensive to feed all these people with my party here, right? We can maybe complain to Wegmans they charge too much for sugar or something like that. Actually, the majority of this turns out to be chocolate chips, as you noticed when you worked it out. Those are pretty expensive, plus we need a lot of them. But the important thing to understand here is that the operations of scalar multiplication and vector addition and dot product are all combined here, and it makes perfect sense in a meaningful way to give us the answer to a very real-world scenario. One more like this. What if I want to know, heavens to Betsy, how much saturated fat I'm going to be serving my party guests if I do all this stuff? How am I going to get the answer? The answer is going to be that. Multiply all of the quantities times the recipe vectors in question, add all those combined things together and then dot product it with a saturated fat vector, and I end up getting this. A whopping 2,864.8 grams of saturated fat is what I'm going to get and serve to my customers. Hopefully they don't die after that. So those are some samples, and you've seen how the three operations work. Here's just a review of the three important facts that you learned. Scalar multiplication with vector addition is distributive, and that just means that those two things are going to be equal to each other always in the first bullet. You can always take advantage of the second fact as well. X plus y is always the same as y plus x, and we're dealing with vector addition. And also x times y is always equal to y times x. You can take that to the bank, always guaranteed to be true.